All right, so the last video focused attention on essentially toxic concentrations of soils from historic mining operations in areas that have a low pH, and how do we overcome toxicities? And we talked about biochar. Well, let's talk about something that's really outside of the spectrum of what you've learned in this class. And so what you've learned in this class with respect to copper, we're going to focus on copper for this video. But what you've learned about copper in this class is as you increase pH, copper availability decreases. What happens if you have a situation where the pH of a soil is rather high and you have a copper toxicity? Oh boy, now this one is a challenge. So we're going to talk about copper in basic soils and how do we fix them. And so in basic soils that contain copper in concentrations that are toxic to plants, there are some things that you could try to do. And so one of the things that you might be able to, and you're not going to likely see this, by the way, very often, unless you're working in a system that adds copper to a basic soil. And then here in Ohio, you're not going to see this, likely. But you might see copper concentrations that are toxic from areas that I'm going to describe in this video. Okay, so keep that in mind. But one thing you could try to do is add excess phosphorus, and that could be in basic or somewhat acidic soils. And we know that phosphorus interferes with copper uptake. You might even form copper phosphate in soils, especially in basic soils, which we'll want to focus on in this portion of this video. And you could add a phosphorus fertilizer or phosphoric acid to supply the phosphorus to offset the copper toxicity. And that might work. The literature tells you that this can work, but maybe it work, maybe it won't work. A better approach is, if you have a problem, to stop adding copper to a soil or to prevent the copper release in the first place. So when you see toxic concentrations of copper in basic soils, in soils above a pH of 7, this is man-induced. It says more than likely man-induced. I wrote that as a academician to cover my butt. This is man-induced. This is not natural. So this is man-induced. And I want to share with you this story. So where can these issues from human-induced copper toxicities in basic soils arise? Well, they can arise from simply spraying herbicides that contain copper. There's a herbicide, or a fungicide, actually. It's not a herbicide. It's a fungicide called the Bordeaux mixture. I believe it's copper. It's either copper chloride or copper sulfate, or you spray copper oxychloride. And I think about fungicides, or I think about copper in the environment. So maybe some of you golf, and maybe you've been on a golf course next to a water body on a golf course that looks blue. And you go, oh, that's pretty. Well, it's blue for a reason. It's blue because somebody added some form of copper to that water to prevent algal growth. Copper will do this, much like a fungicide. Copper will prevent algal growth in a water body. And that's why if you're on a golf course and you see a very blue color in water, it most likely has been treated with copper. In acidic soils, we may find copper toxicities. And this could be man-induced simply because of fertilizers or pesticides, or, it doesn't say this here, from historic mining operations that have led to the exposure of fool's gold, ferric sulfide, that has been oxidized over time and has formed sulfuric acid that has degraded rocks and minerals that contain copper. And you may see copper toxicities from humans under hog or poultry manure land application, because sometimes copper, and sometimes zinc, but sometimes copper is added to the diet to increase food conversion and improve growth of hog and poultry. And so you may see this in situations or systems where that liquid or solid manure is added to a soil, and this is what you would see on the bottom right-hand corner. This is a copper toxicity symptom where the leaves just sort of turn brown. It's hard to tell, but they may look chlorotic and look like an iron deficiency, and it manifests itself over the entire plant. Where else can this occur? So I want to share with you a story about Idaho. I spent 10 years of my career in southern Idaho, where this is what happened with the dairy population. It sort of bounced along around, this is in thousands of head of dairy cows. It bounced around 200,000 head. In the late 1990s, it took a steep rise. And right now, there's somewhere between, I don't know, 550,000 to maybe 600,000 head of dairy cows in south central Idaho in about a 60-mile, maybe 60-mile radius. Yeah. So a lot of dairy cows. And the shift to dairy production in this area of the United States occurred because, unfortunately, this state had relatively lax regulations with respect to the dairy industry. And so dairies moved to this area because of that. That's neither good nor bad. It just happened. Okay. And so think about, how does this relate to copper at all? And so in the dairy industry, oftentimes what happens is, these cows come into a milking parlor, they're milked, and then when they leave the milking parlor, and this doesn't happen often. I mean, doesn't happen all the time, but it certainly happens in dairies that I've worked on, where these the cows walk through a hoof bath, and they walk through a hoof bath to prevent or help prevent hoof diseases. Why in the heck would they have hoof diseases? Oh, okay. Maybe you don't know this, but these are confined animal feeding operations, and these animals are standing around in all sorts of materials. All right. So it's standing around potentially in wet materials, poop, wet soil, etc. A haven for disease. And if you have a hoof disease in an animal that is producing anything, a disease will lessen the productivity of that animal. And so to offset that issue, animals oftentimes walk through a hoof bath. And in this case, not all cases, but in this case, this is copper sulfate. And just like the story that I told you about the golf course ponds, this helps to prevent disease. And when that hoof bath is spent, when it's no longer functional, guess where it goes? Oftentimes it goes sight unseen and is dumped into a waste lagoon. And in this area of the US, like other areas of the US, that waste lagoon water, although it may be thick, it's oftentimes cut with clean water and then used for irrigation purposes. And that irrigation typically occurs very close to the dairy itself. And so the concept here is to stop this from occurring altogether. So this is what we see in these fields. And somebody brought this issue to me, a number of years ago, where fields like what you see in the top left-hand corner, or what you saw on the previous slide, are being irrigated with dilute wastewater effluent that contains copper. Okay. I can tell you that the copper concentrations are in that water. The copper concentrations in terms of available concentrations are not that great, but they're great enough that over time, copper builds up in the soil. And copper loves to form associations with clays and especially organic materials. And copper tends to not move in the soil. It stays where you place it. So it stays in the upper profile. And so when you're planting seeds, like in the pictures that you see here, corn, sometimes the corn suffers because it sees a copper toxicity, like the corn in this row here. It is stunted. The leaves are spindly. They look like they're suffering from maybe a drought condition, but that's because of copper toxicities causing spindly leaves and stunted growth. And sometimes you see some leaf burn with this. Leaf burn is oftentimes associated with toxicity. When the toxicity is really perceived in a field, it looks like a deficiency. So you can see the deficiency in these two pictures of corn. and it looks like an iron deficiency. It looks like there's intervenal chlorosis. You may not be able to see it in the picture here, but if you were to rip the plant out, and I've shown you these pictures already, at least the two pictures on the middle and right-hand side. These two corn plants came from a field much like what you see in the bottom left-hand corner. But it's not an iron, it actually is an iron deficiency, but look where the deficiency manifests itself. If it was a true iron deficiency, it would only manifest itself in the younger leaves, but it's over the entire plant, which tells you something else is occurring in this field. And in this field that has a pH of 8.4, this is a copper toxicity. So I've shown you some of these pictures already. This one on the left-hand side, the normal roots look kind of normal, and the affected roots look stunted. They're not filled in, and they're darker brown. And in fact, if you were to look at, and this is not from this study, but a normal root should look something like this, and affected roots look stunted. The apical meristem is simply not growing. The lateral roots that are coming off look horrible. They look short and stunted, and the overall root system looks darker, much like this picture of this corn root here in the left-hand side, or the right-hand side of the left-hand side of the picture. So it's interesting to note that when you dive a little bit deeper into what's happening, this graph tells you some interesting things about what's happening in this portion of those fields. So on the y-axis is copper concentration in the plant. And let's focus on normal shoots, and this should be normal shoots, contaminated shoots. Okay, let's do this. I haven't looked at this in a while, but the normal shoots. Let's focus on the normal shoots and the normal roots in terms of copper concentrations. So the normal roots have a copper concentration of maybe about 10, and the normal shoots have a copper concentration of maybe 5. And what do we see in the contaminated roots and the contaminated shoots? The contaminated shoots tell you that there really is not that much copper present, right? The contaminated shoots, there's not a lot of copper present, but the contaminated roots, oh my gosh, there is 160 parts per million copper in the roots. And this tells you something about what's occurring in the plant. Let's look at corn iron content, right? And this tells you more of the story, and then we can put this puzzle together. So this is iron concentration on the y-axis, and in the normal roots, the iron concentration is relatively high, and in the normal shoots, the concentration is relatively low. In the contaminated shoots, the iron concentration is actually relatively low. It's actually very similar to the normal. But in the contaminated roots, the iron concentration is low. And so the combination of both of these graphs here tells you a little bit of a story. And it likely tells you that there is some sort of interaction between copper and iron, right? And it happens in the roots. It really happens in the roots. And the copper concentrations in the roots are astronomical, and that leads to a reduction in iron concentration in the roots. And subsequently, the concentration of iron that manifests itself in the shoots, although it looks normal in terms of the concentration, it does not look normal in the picture that I share with you several slides ago. And so this is also an interesting story about copper. And in copper, much like other micronutrients, when they become toxic, the plant sees the toxicity and tries to prevent the toxic concentration of that nutrient from being translocated from the roots to the shoots. And so the roots suffer because the root system is smaller, the concentration of, in this case, copper builds up. We can also see this in the soil. And so the left-hand side graph shows you copper in quote clean soil and contaminated soil. And this is total soil copper. In clean soils, total soil copper concentrations are, in this case, about 8 parts per million. And in the contaminated soil, it's up above 50. So there is an issue here, obviously. And if you look at the right-hand picture or graph, this on the y-axis is essentially plant available copper. In the clean soil, it is about 2 parts per million. That's relatively normal. And in the contaminated soil, it's not quite, it's probably what, 23, not quite 25 parts per million. This is an issue. And this is why we see the issue with corn copper contamination in this system. So how do we solve this problem of the hoof bath waste being dumped into a waste lagoon and that waste lagoon water being used for irrigation? Well, first, you try to stop this from occurring in the first place. In the soils that are affected already, there's several things you could try. And I was about to try this when I left this position, but adding phosphorus fertilizers to this soil to reduce the uptake of copper into the plants by simply binding copper to phosphorus. And it says use increasing application rates to target optimum rate of phosphorus fertilizer for plant copper uptake reduction. That's where we were going with some of the research. You could try to just simply, instead of putting that wastewater effluent, the hoof bath waste into the wastewater effluent, divert it into maybe a secondary system that could sorb copper. And so one of the things we were working on where I used to live was mixing that waste liquid in the top right-hand corner with lime waste. And so in this area of the US, there was a sugar beet factory that generated a heck of a lot of lime waste from the production of sugar. And that's what you see in the left-hand picture here. This giant white pile, and in fact, it looks like there's some grass growing on this as well in some areas. That's all lime, that's sugar beet lime waste, either uncovered or covered with grass. And it's lime. And we know that lime, when you add lime and in the presence of copper, you can probably form copper oxide or copper carbonate or sometimes copper hydroxide. And so what we did was we did a simple study. And I'm only showing you a portion of the study of the amount of copper added in solution on the x-axis versus copper adsorbed onto that lime waste. And there's a dotted line, which is a 1-to-1 line. And then the circles, the blue circles represent the amount of copper adsorbed onto the lime waste. And it follows this rise to a maximum. And the line that is fitted within those blue circles tells you something. And here's the equation, and it's an exponential rise to a maximum equation. You don't need to remember that. You don't need to remember any of this. This is just all FYI, by the way. But the number here, 44,640, that's the amount or parts per million copper that this material can absorb. And so that is quite a bit of copper. The hoof bath waste typically contains about 12,000 parts per million copper. And so if you mixed a known amount of hoof bath waste with a heck of a lot of lime waste, which is generated on a large scale, you could likely sorb all of that copper. And then the next step would be, and I don't have this on this slide set, but to regenerate copper sulfate from the lime waste that has absorbed copper and use that copper sulfate back as a hoof bath material. Interesting. And so with that, this brings us to the end of this course. I want to thank all of you for putting up with video after video after video of me talking to you, big talking head. But more importantly, I hope you learned something throughout this course that can be useful for you in the real world and in your careers. And I appreciate all of you and the time that you've spent. Thank you.